what's important to mention is that the strength of the graph neural network is really that it captures the shape of the contour. So it's really robust towards changes and doesn't have any severe outliers like classical segmentation approaches. And it's also in this implementation quite lightweight and fast. I have the pleasure to speak a bit about a quite recent project that we're working on. Before I start, let me quickly introduce myself. I was born and raised in a little tiny village in Germany and have a rather interdisciplinary background in medical engineering, but also in robotics at different locations in southern Germany, but also in Canada and China. I did my PhD in medical informatics at the German Cancer Research Center, where we worked together with Siemens on deep learning applications for bone surgery. And finally, last year in August, I took the ferry all the way up to Norway to start a new position as a postdoctoral research fellow at the University of Oslo in the DSB group, working together with GE Healthcare on the so-called EchoAI project, what Anna mentioned. Some details about the EchoAI project, short for echocardiography diagnostic interpretation system, which is a 4-year innovation project funded by the Norwegian Research Council, which has different research positions, and the project is owned by GE WingMed, coordinated by Eric Steen, and together with the Norwegian Computing Center and us, the University of Oslo. And the overall purpose is developing automatic diagnostic measurements for cardiac ultrasound images. We have a quite broad range of ongoing projects now in the field of view recognition, timing, but also what I want to talk about today, measurements on 2D image sequences. Before I come to the project as such, I want to start with the clinical motivation of the project. Why are we doing this and why is it important? So one really critical medical condition is the so-called heart failure. When I first heard the term heart failure, I thought that heart failure would mean your heart fails to perform and then you die, but it's a bit broader. So heart failure describes any condition where your heart is unable to pump enough blood through the body. And the symptoms are like highly vary. So I read about dizziness and about swollen extremities, about problems breathing. And similar to the symptoms, also the causes can highly vary. So it can be a problem of your arteries, but also high blood pressure. It can be a problem of your muscles, a problem with the rhythm of your heart beating, but also a problem of your valves, some defects, or congenital heart diseases, so meaning conditions that you are born with. And heart failure is, whenever I read papers about it, I always read the sentence, heart failure is one of the leading causes of hospitalization in the US. I would say that this is more or less true for many other industrial countries. I tried to look it up for Norway, took me some time. What I found is that at least in 2020, 2,000 patients were hospitalized with heart failure. And I also read that the survival rate is only 50% after 5 years, which means that heart failure is like highly critical, and costs a lot of money and for the healthcare system. So no matter if your GP sends you to the cardiologist based on the symptoms you're having, or if it's that severe that you're sent into the emergency room right away, the tool for estimation or for acquiring whether you have a heart failure is the most commonly tool is always diagnostic ultrasound. This has several reasons. So not only that ultrasound is well suited to find most of the different pathologies of the heart, it's also really fast and cheap compared to, for example, MRI or CT. It's more available than those huge scanners and highly versatile. Is not as invasive, or it doesn't include radiation as, for example, X-ray does. And what's also really nice about it is it provides dynamic measurements. Since the heart ideally is highly dynamic, this is really important for heart diseases. So now, how to measure, how to obtain an ultrasound image. During the image acquisition, the probe is usually positioned at specific positions in your body. This is, of course, not random. The probe needs to be positioned precisely so that you have a good view on the key structures you want to look at. For example, if you would put the probe here, this is called the apical window, then you could obtain something like this. This is called 4-chamber view, because you have a nice view on all 4 chambers on the ventricles, but also the left and right atrium. And so speaking about heart failure, one of the very important indications for heart failure is the so-called ejection fraction. Not all causes of heart failure, or not all types of heart failure, are related to a reduced ejection fraction, but ejection fraction can give a good and important indication for it. So what is ejection fraction? Ejection fraction is basically the proportion of blood pumped out of the ventricle during contraction. So the highest volume compared with the to the lowest volume that your ventricle holds. And whenever you look at different sources, you find different values. So I had quite a hard time to find the exact values for that. This source, for example, tells that if the ejection fraction is below 53, then you should take care of it, or you should definitely see your doctor. If it's below 30, then you really have a problem. So I said now what ejection fraction is, how to measure it, given that we obtained this image I just showed. So this is not an image, but an image sequence. And this image contains the whole heart cycle, or multiple heart cycles. So what we first need, as I said, the ejection fraction is comparing the highest volume and the lowest volume of the ventricle, held by the ventricle. So we first have to find the frame with the highest and the lowest volume, and those are well defined, and diastole and systole. And on those frames, the cardiologist now contours the left ventricle to estimate the outer contour and to estimate the area. And the ejection fraction is now defined as the proportion between the and diastole volume minus the end systole divided by the end diastole. As I said, it's about volumes. Of course, a 2D image or the contour you obtained is not a real volume, but there are methods to approximate the volume out of it. And the most recommended method, also by the guidelines, is the Simpson's method, which fits disks into the area and computes a volume out of it. And in ideal case, you perform that measurement on 2 different views, like not only the 4-chamber view, but a view that it's not orthogonal, but with a quite large angle towards the other view. And in ideal case, as the guideline recommends, you average it over multiple cycles. So you would contour the left ventricle in multiple cycles and then average. In reality, it looks a bit different. So I spoke to different cardiologists, and it really depends on the available time and resources. So I actually observed some cardiologists, and I haven't seen that they contour multiple cycles. They rather pick a good one and perform it on only one. And I also talked about to cardiologists in different countries, and they said they don't even perform it on 2 planes. They just perform it on one, or it really depends on their resources, because they have so many patients and they just don't have the people for it. This, together with the fact that contouring is not so trivial and really depends on the image quality and the cardiologists, leads to a high inter and intra-rater observer variability. So although this ejection fraction is so critical and so important, we still have the problem that it's really hard to compare values. And those 2 reasons make the medical image processing community awake, and leads to the need that people are working on automatic measurements on ultrasound images in recent years, also using artificial intelligence, with the aim to make those measurements automatic, so fast, and also like more reliable or more standardized. And so to summarize the application, what we can do is estimate the contour of the left ventricle. This is not only for ejection fraction, but multiple measurements can be derived from that contour. But if you contour the ED and ES, the diastole and systole value, you could also compute the ejection fraction from it. The ejection fraction, as said, is one important clinical measure. What I want to mention here as well is that for the clinical data we usually have is that we have like this image sequence. This image sequence can be 1 cycle, but also multiple cycles. But we almost always only have 2 frames annotated. So 1 frame for each key frame, and all the other frames are unlabeled. So for the whole sequence, only 2 frames available. And when you look at the state of the art of automatic measurements for contour detection, the way to go really is segmentation, automatic segmentation, and then derive the contour. So there are many works done on automatic segmentation. One I want to mention here is a group from Trondheim, from NTNU, who which really did nice work, and they also published a paper on ejection fraction based on the contour or the segmentation of left ventricle images. Yeah, as I said, they not only published a paper on segmentation, but also derived the ejection fraction based on the segmentations. What you can also do is you can directly regress the ejection fraction. There is a recent work from 2020 from Ouyang using spatial temporal CNNs for it. But even more recently, last year, MICCAI, there was a paper published directly regressing the EF based on transformers on image sequences. So the two last approaches I mentioned are more or less black box approaches because they directly regress the EF and do not care about the contour. And the first approach I mentioned is basically a two-stage approach where you first have the segmentation and then the EF. And we were wondering for this project whether we can have one network that predicts both at the same time. And that's why I now have the pleasure to introduce our latest project on graph-based contour detection and EF computation. So it's all based on graphs. This was really a team effort between Guy Van Josef from GE Research, me and Andy Gilbert from GE Wingmet. It was not only multi-institutional, but also multi-international. Guy is located in Israel. I am in Oslo, and Andy at the time was in Chile. So it was not only technically demanding, but also time-wise to find a good time to work on it. Before I introduce our architecture, I want to quickly introduce what a graph is. Let's start from the beginning. So probably some of you know that a graph represents relations called edges between entities called nodes. What does that mean? So each of the things I just mentioned can hold information. And let's say that we, as a start, want to model Facebook as a graph. Then each node is a user, and let's say that user is you. Then each node, each user can have certain features. So on the one hand, the features, in the most easiest case, your name, but also all features that you provided to Facebook or that Facebook got from you. And each edge represents a relation to others. So in the most easiest case, it would be the relation friend or no friend. Mathematically, you can formulate that as a adjacency matrix. For each entry would be the relation between one node and the other. If it was a 1, then you're our friend. If it's 0, then you're not friends. And this is the most easiest case, but of course you can model anything you want. You can model the more complex relationship between users and whatever you want, basically. And also the graph can have features. So given that Facebook is a graph as a whole, it can also have subgraphs, and the subgraphs could have features like likes fish or plays piano. So that allows like a high range of modeling opportunities. And applications for graphs are like manifold. besides the social media members, you could also model a road system with streets and cities. In the medical domain, I think it's worth mentioning, two examples are worth mentioning. One is that in the last 2 years, protein structures gained lots of attention because deep learning researchers were really successfully able to model the 3D structure of proteins. And another example, I would say, where graphs started in medical imaging was functional brain imaging, where you look at how different parts of your brain affect others. Now that we have described the graph, how can we use it for a graph neural network? So for that, I first want to look at classical neural networks for image classification. When you look at this image, your brain and also your trained network immediately recognize that this is a snowman. But how does it work? Like this image contains, or images in general contain so many information, all the pixels contain information, but how to get from this huge stack of information to one label. This is done also by your visual cortex, but also by the network, by iterating over the image in patches. So your network or your visual cortex doesn't look at the whole image, but iterates over the image and learns how it needs to compress the data to get to a more dense representation. And if you do that for different levels and compress the data further, you can get from one image to one label. And what's really important to mention here is that this always assumes that neighboring pixels are neighbors when you process them. So imagine you would shuffle all the pixels of the image. Your brain would never have guessed that this is a snowman. And this is the same for the network. So neighbor relationships have to stay. How about the graph neural network now? So imagine you would model an image as a graph. Then you would have nodes for each pixel or for each super pixel. It doesn't matter how do you define it, but important is that edges would be only shared to the direct neighbors, not to arbitrary nodes in the graph. So changes of one pixel only affect the neighboring ones. And but for a graph, this is more generic. So you can define whatever you want. As long as you know how your graph is structured, you don't need that specific strict relation. So you can do whatever you want. And for each node, the nodes, only the nodes around this node connected with an edge are affected. And this way, you can also define the graph neural network similar to, for example, CNN, that you have different levels where you process the data, with the difference now that not neighboring pixels are connected or compressed, but the information based on what, for example, your adjacency matrix or what your edge information set. And with this, you can not only model where in the image the face of the snowman is, but you could also classify that this is hopefully a happy snowman. Now we process the snowman back to our original problem. So in image, there are different definitions how you can design your graph neural network. For processing images, one way is that I mentioned in the beginning that each node of the graph needs certain features. And how to get those features? One way is to get from the image to a certain feature representation. And since, as I said, the image contains way too much information, one way to deal with this is to have an CNN as a backend and convert the image into a feature representation, and then assign the feature representation to the nodes, and then process the nodes in the decoder to get a certain output. Given that we want to solve the problem that I mentioned in the beginning, in our case, we have an ultrasound image or ultrasound sequence as the image. As a graph, we have a quite well-defined graph because we want to estimate the contour of the left ventricle. So our graph has a more fixed topology, which is quite well-defined. And as an output, we would ideally have for each node a 2D coordinate where in the image it is located. And since we have this unique and well-defined topology, we applied a principle that we found from, or that was applied in general computer vision. It's called spiral convolutions. The thing about spiral convolutions is that neighboring nodes are always processed in a fixed order. So what you see on the right is taken from a closed 3D mesh. So you would start from one point, and then you define your neighboring connections as a fixed spiral order, as a fixed spiral sequence. The main advantage of this is that it introduces a sort of inductive bias because it's always in the same way. And it needs to be established only once in the beginning, because you do not change it over time, which allows a very efficient computation during the message passing between the different levels. Stacking or plugging in the spiral convolution, that's our network decoder, looks like the following. We get the input of the CNN encoder, and then we first need to further compress it to get the right size for our decoder. Then we have also those different layers. Each layer is this spiral aggregation, and then an MLP to process the features further. And what we get in the end is a quite dense feature representation where each, in this case, 12 key points get two features, the X and Y coordinate. This is the architecture, and we came up with two configurations. One configuration is we call it single frame approach, where we input one single image, then have a image encoder as a backend. And with that, we can predict the contour key points of the left ventricle. This approach we compared with standard segmentation approaches that were used also for computing the segmentation also used with the same data sets to have comparable results. Another approach that we implemented is the multi-frame approach. This time you can see that we don't have an image, but a whole sequence. And this time we use a video encoder to compress the features. And with this and we changed the encoder. This time we not have like a single graph for the contour, but we have multiple graphs that have interconnections between the different time points. And with that, we can predict two contours, the two contours of the keyframes. And those keyframes together would allow us to predict the ejection fraction as well. This worked quite well, but we also experimented a bit if we can further improve it. And it turned out that we obtained quite good results when we added another head to after the CNN encoder, besides the graph, that was optimized together with the graph, but directly could output the ejection fraction. This, what I so far explained, always assumes that you have one heart cycle with known ED and ES. But this is not always the case. So sometimes or often you don't have this information where the ED and ES frame is. So we added another head that was able to predict also where the frames, or if there are key frames in the image. And with this information, we could even insert random sequences and predict the ejection fraction, the contours, but also whether there is a ED and ES frame present. And we evaluated that on a public data set called EchoNet. There are over 10,000 image sequences with annotated ED and ES frames. I said in the beginning that only 2 frames are annotated per sequence, no matter how many cycles you have. And each frame had annotated contour points, like you see in the bottom, to describe the contour, but also they provided ground truth values for the EF. And with that, we evaluated the approach, what you can see here. I mentioned last time when we had Fabian Niesensee presenting that I think that the NNUnet cannot be beaten. I might have said that because we also tried and failed. So the NNUnet still couldn't be outperformed by our approach. But we got in quite close proximity with different backbones, different encoders, and we could show that we could achieve a quite high accuracy and be way more faster than the other approaches with less parameters. So that was at least a good thing, and really is really important also, especially when you talk about like real-time applications. Speaking about the EF estimation, we compared with the baseline approaches that I mentioned in the beginning, the paper from Stanford and the transformer paper, and we compared to the configuration with the single heartbeat, as well as with the whole video without any information about ED and ES, and we could show that we got really good results. At least with one configuration, we could outperform the other approaches, and we could show that using a graph together with the regression head is better than the regression only, and better than using the key points as such. So the best configuration was optimizing both. So to sum up the results, as Anne mentioned, we are happy that it got provisionally accepted at MICCAI 22. As I said, it almost reached the accuracy of the classical state-of-the-art segmentation approaches, and was among the fastest. For the ejection fraction, we obtained same or even better results than comparable models. What you can see here is the model applied on the whole sequence. So not only applied to the keyframes, but to the whole, to all of the images. And as you can see, it's quite consistent over time, which also leads to the conclusion. What is important is that the network was able to simultaneously predict contours and EF, with the downside that we still, for the best configuration, had two heads. So in the future work, we probably would like to work on having even one single head that can predict both to make it more explainable. But right now, the best configuration is with those two heads. What's important to mention is that the strength of the graph neural network is really that it captures the shape of the contour. So it's really robust towards changes and doesn't have any severe outliers like classical segmentation approaches. And it's also, in this implementation, quite lightweight and fast. So that was it for this project.